35th lecture, and the topic is small signal amplifiers. As I had drawn last time, a typical BJT amplifier, a complete BJT amplifier looks like this. Let me draw it once at least. RE and CE, there is an RC, and this voltage is plus VCC. The load is coupled to the transistor by means of a capacitor called CC2, coupling capacitor number 2, and this is RL, the actual load. The signal voltage is taken from here, and obviously this voltage shall be purely incremental voltage or the AC voltage. Now we have adopted the notation that if I say VBE, this is the total base emitter voltage, this is equal to the DC base emitter voltage V, capital V sub capital VE, plus small v sub small b small e. This is the AC input voltage. Now we shall adopt the notation, we have already done that for the signal part the root mean squared value shall be denoted by the RMS value of VBE, if it is sinusoidal, shall be denoted by capital V subscript small b small e. For example, if we are concerned with the collector current I sub capital C, well, it is the sum of I sub capital C, this is the DC value, plus small I subscript small c, this is the AC value, and the RMS value of this shall be denoted by capital I subscript small c. Okay. This is the notation that we shall follow, and therefore what should we call this voltage? This voltage root mean squared value. We will only write root mean squared values now. It should be called V sub small c, then that is all. It is the voltage of this point with respect to, no, with respect to ground, because CE is short. CE makes RE short, and therefore this is the voltage. Okay, VCE or VCG ground is the same thing. So we shall call it VC, simply VC, all right, and we will note down a polarity. This polarity shall be a relative polarity, all right. For example, if V sub capital B is positive, then you know that V sub small c shall be negative. There is a phase change. Well, this will be clear in the subsequent discussions. Then the base circuit is biased by means of R2 and R1, and the base circuit is coupled to the voltage source or current source. Let us represent this by a general source. A general source has an internal resistance RS and a voltage. If it is AC, then we shall say small v subscript small I, V input, or small v subscript small s. And if I want to only write the RMS values, we will write this as capital V subscript small s. We shall follow this discipline throughout. For example, the AC base current shall now be denoted by capital I subscript small b. That means the root mean squared value of the signal voltage. And as I have repeatedly told you, we can divorce signal quantities from DC quantities, and therefore we can analyze by means of the small signal model of the transistor. There are three capacitors here, CC1, CC2 and CE. Two of them, CC1 and CC2, are coupling capacitors. They couple the AC to the transistor. This couples the voltage, the collector voltage, to the load. So there are coupling capacitors, and C sub E is a bypass capacitor. It bypasses the AC to ground so that nothing drops across R sub E. Now if I follow the hybrid pi model strictly, then my AC incremental equivalent circuit would be like this, and try to draw with me. What we have is, we are representing every quantity by means of its RMS value. So Vs, then an Rs, then a CC1, the coupling capacitor, and then as far as AC is concerned, from this point to ground, R1 and R2 come in parallel, and we have chosen to call R1 parallel R2 as capital R subscript capital B, RB. RB is the parallel combination of R1 parallel R2, parallel combination of R1 and R2, alright, RB. Then comes the base, from the base to the emitter, it is R pi, alright, it is R pi. Then RE and CE, well, that there is a parallel combination. We will see the effect of this. RE and CE, this terminal comes here, alright, RE and CE, and then this voltage, if I call this voltage as capital V, this voltage is capital V, voltage across R pi, then at the output you have GM times capital V. This is the collector terminal, and from collector to ground, goes a resistance R sub C, and then from the same point collector, a capacitance CC2 goes to RL, and this voltage is V sub C or V0, the output voltage. Okay. So, in order to determine the performance characteristic of this amplifier, that is the amplification property, what we have to find out by circuit analysis, we have to find out V0 by Vs. That would be the gain of the circuit. We have to find, and in general you see, because there are resistances as well as capacitances, this gain would be a complex quantity. It would be a complex quantity. You will have to replace the capacitors by 1 by j omega c. To be fair, to make this circuit applicable at all frequencies, we should introduce the terms, the capacitances which are internal to the transistor. If this circuit is to represent high frequencies, for example, we should introduce the C pi. C pi is across R pi. C pi, and another capacitor we should introduce between this point and the collector. This is C mu. Alright. If we introduce these two, then this circuit is complete. It can represent low frequencies, it can represent high frequencies, it can also represent medium frequencies. And the most convenient calculation for gain comes at medium frequencies. At medium frequencies, well, the frequencies are defined, medium frequencies are defined as the frequencies neither too low nor too high. These are frequencies at which the effect of capacitances can be ignored, which means that at medium frequencies CC1, CC2 and CE should act as short circuits. Medium frequencies are those at which CC1, the two coupling capacitors, and the emitter bypass capacitor, all the three act as short circuits. And the internal capacitances, which are very small, at medium frequencies they act as open, that is C mu and C pi, they act as open. And therefore, at medium frequencies, which is also called the mid band, our equivalent circuit, if we follow this carefully, our equivalent circuit would be Vs, then Rs, Cc1 will act as a short, then we shall have Rb in parallel with R pi. Now R pi comes across Rb because Re is a short, Ce is a short, and therefore R pi comes across R pi. R pi comes across Rb, and this voltage is V. Okay. Then we have GMV, no capacitances, C pi is ignored, C mu is ignored, and we have GMV in parallel with R sub C. Then the capacitor CC2 also acts as a short circuit, and therefore this is R sub L, and this voltage is V0. This is the situation in the mid frequency range, sometimes called mid-band equivalent circuit, mid-band frequency range. Well, I should mention here that if you plot the gain, that is if you plot V0 by Vs versus frequency omega, then in general for the RC coupled amplifier the curve looks like this. That is at DC the gain is 0. Why is it 0 at DC? Because these coupling capacitors refuse to pass DC. Alright, this coupling capacitor, this coupling capacitor. So at DC nothing reaches the transistor doesn't amplify. Alright, that's why the gain is 0. As the frequency increases, these two capacitors they become less and they offer less and less impedance, and therefore signal passes to the amplifier, to the transistor, and the transistor does amplify, so the gain rises. Then around, let us say there is a set of frequencies at which the gain is a constant. The gain can be a constant only if there are no capacitances in the circuit, which means that this is the mid-band frequency range. This is the mid-band range, and then as the frequency is increased, the coupling capacitances and the bypass capacitance, they remain short because the impedance is 1 by j omega c. So the higher the value of frequency, the lower is the impedance. They remain short, but what we had assumed as open, that is the two internal capacitances C pi and C mu, they now show their teeth, and therefore their effect then dominates, and it is because of these two capacitances that the gain once again falls. Alright, so it is a bell shaped curve. This region, the region from 0 to the beginning of the mid frequency, is denoted as the low frequency region, and the region, the frequency range from the end of the mid band to infinite frequency theoretically is the high frequency band. And you know that in such a characteristic, not only the mid band gain is important, mid band gain we shall denote by A0, but also the two frequencies at which the gain falls below the mid band value by 1 by root 2, and therefore this value is A0 by root 2. There are therefore two frequencies, one we call omega L and the other we call omega H. Omega L is called the low frequency cutoff, this is the frequency, and omega H is the high frequency cutoff. That means between omega L and omega H the gain remains within 70.7% of its mid band value. I have also told you that the gain is usually expressed in terms of decibels, and the decibel gain is 20 log 10 of A, and 20 log 10 of 1 by root 2 is approximately minus 3, and therefore if the mid band value is taken as the reference, then this level is 3 decibels below the mid band value. If the mid band value is taken as 0 decibel, then this is minus 3 dB, this point and this point. Is that point clear? Did I not discuss decibels earlier? Oh, I didn't. Okay. The gain, you see, the gain could be a very large quantity. It may vary from 0 right up to, let us say, 10 to the 5 or 10 to the 6, and it is very difficult to represent such a large dynamic range, and therefore what you do is you compress the range by a logarithmic transformation. For example, if capital A varies from 1 to, let us say, 10 to the 5, then at 1 the value is 0, 20 log 10A, and at 10 to the 5 it is simply 100. So what you represent is 0 to 100 instead of 1 to 10 to the power 5. So you compress the range, and therefore gain is always, in electrical engineering practice, gain is expressed in decibels, decibels, and it is written as d small d capital B. The definition is that this is 20 log 10 of gain as a number, alright, 20 log 10A. And you see, if the gain is A0 by root 2, then it is simply, as you know, 20 log 10 A0 minus 3, half of log 2. Log 2 is 0.30103. Alright, is this clear? 20 log 10 A0 minus 20 log 10 of root 2. 20 log 10 of root 2 is approximately 3. Actually it is 3.0103, we ignored that. And therefore these are frequencies, omega L and omega H. These are frequencies at which the gain is reduced by 3 decibels, and these omega L and omega H therefore have got another name. One of the names is low frequency cutoff, high frequency cutoff, or they are also called 3 dB points. That is the frequencies at which the gain is down by 3 decibels, 3 dB points, omega L and omega H. Alright, we shall calculate what omega L and what omega H is for the RC coupled amplifier, but at the present time we are concerned with the calculation of the mid-band gain. Mid-band frequency range by definition is one in which the effect of all capacitances can be ignored. The coupling and bypass capacitances are shorts, and the internal capacitances C pi and C mu are open. Alright, if that is the case, then this becomes the equivalent circuit, and we simplify the equivalent circuit by noting that RC and RL are in parallel, and we can replace this by R0. Let us call this R0 as equal to RC parallel RL. You also notice that RB and R pi are in parallel, and if RB and R pi are comparable, then you can combine the two and you can call the resulting one as R pi prime. But the usual design consideration is that RB is usually much greater than R pi. R pi is of the order of a k, and RB would be of the order of 10k, and 1:10 can be considered as much greater than. And therefore in our subsequent calculations we shall ignore the effect of RB. If needed, if your design is such that RB is comparable to R pi, then you simply combine the two. That is, you take instead of R pi, you take R pi prime, which is the parallel combination of RB and R pi. And therefore our circuit, our equivalent circuit, then simplifies to the following. We have a Vs, Rs is the source resistance, then we have R pi, this voltage is V, then we have GMV, and simply R0, this is equal to V0. And you notice that the gain A, we are calculating the mid-band gain, and therefore I put a subscript 0. A0 is V0 by Vs, which I can write as V0 by V multiplied by V by Vs. Is that okay? V0 by Vs I have written as V0 by V multiplied by V by Vs. What is V0 by V? You see, this current flows through R0, and therefore V0 must be equal to minus GMV times R0, and therefore V0 by V is simply minus GM R0, and V by Vs is simply a potential division, that is R pi divided by R pi plus Rs. And you see that GM and R pi come as a product now. The product is beta, and therefore I can write this as minus beta R0 divided by R pi plus Rs. You can see what happens if capital RB is not, it cannot be ignored, then R pi shall simply be replaced by R pi prime, which is the parallel combination of R pi and RB. So this is the simple formula for the mid-band gain, that is minus beta R0 divided by R pi plus Rs. Let us take some typical values. For a certain transistor 2n series, beta is typically 100, the source resistance typically is 1K, 1000 ohms, Re is of the order of 500 ohms. Re does not enter into the mid-band calculation because Re is shunted by a capacitance which is sufficiently large. R1 is 20K, R2 is 50K. Therefore, Rb is how much? 20 times 50 divided by 70, that is 14.3K. Alright. Rc is, let us say, 4K, RL is 4K. So that R0 is simply equal to 2K. R0 is the parallel combination of the two, and I sub C, the collector current, is given as 2 milliampere. Alright. You are required to calculate the mid-band gain A0. Obviously, for mid-band gain calculation, minus beta R0 divided by R pi, you understand the meaning of the minus sign, because the output voltage is out of phase with the input voltage. Okay. R pi plus Rs, therefore you need the value of R pi. We have been given the value of beta, and we know what is I sub C is, that is the quiescent collector current, and therefore we can calculate the value of Gm. Gm is 40 times I sub C. Therefore 40 times 2 times 10 to the minus 3, which is equal to 0.08. Is that okay? And therefore what is R pi then? Beta divided by Gm, therefore 100 divided by 0.08. Have I made a mistake? So how much is this? 1.25K. All right. That's correct, 1.25K. And you notice that indeed 1.25K R pi is small compared to RB, which is 14.3. One order of magnitude difference is good enough for much greater than. So we can indeed ignore this. Now if we substitute these values in the mid-band gain, then I get A0 I get A0 as equal to minus 100 beta, R0 is 2K, 2 times 10 to the 3 divided by R pi, which is 1.25 times 10 to the 3 plus Rs, which is 1 times 10 to the 3. So 10 to the 3 can be ignored. This is minus 200 divided by 2.25. Is this minus 800 by 9? Yes. And as you can see, this is approximately equal to minus 90. Alright? Approximately equal, it's slightly less than 90, 89 point something. But this is the typical mid-band gain. You can get a gain of 90 to 100. And if you couple another stage, you can get 8100 gain, 90 times 90. Alright, very large gains are indeed possible. Now let us look at, this is the mid-band situation. Mid-band situation, as I said, is the situation in which the gain remains approximately a constant. Why does it remain a constant? because the effect of capacitances can be ignored. All right. Let us look at the low frequency situation. What happens at low frequencies? At low frequencies, the internal capacitances of the transistor can be ignored, but the coupling capacitances must be taken into account, and also the bypass capacitance. Now, since there are three capacitances to be taken into account, three capacitances CC1, CC2 and CE, circuit analysis becomes a bit complicated. Also, one tends to get lost in the mathematics or the algebra of the situation. One tends to get lose sight of the physical situation. So, what we will do is, for an engineer, is very important, very convenient to consider one at a time, one effect at a time. We shall be a little more prudent, we shall be a little more flexible, we will say two at a time. Let us take the effect of CC1 and CC2 into effect, which in effect means that CE we are assuming to go to infinity. The largest possible CE we put there, and therefore we look at the effect of CC1 and CC2 only. And if you draw the equivalent circuit, then the RMS value of the signal RS, then there is a CC1, the coupling capacitance. We have the R pi, and this voltage is V. You see the advantage of having V instead of current, I sub B. Then we have GMV, and we have GMV in parallel with RC. Then we have the second coupling capacitor CC2 and the load resistance RL. This is V0. Now, unlike the mid-band situation, we cannot combine RC and RL because CC2 is not a short. It offers appreciable impedance. The impedance can be comparable to that of RC and RL. Therefore, we cannot consider this. But we can do one thing very interestingly. We can replace this part by Thevenin's theorem, and therefore what we can do is then RC and RL will come in series. You see the point? So, what we can do is this part I can write as GM V times RC. This is the open circuit voltage with what polarity? Minus, plus. Then the Thevenin resistance is RC. Then we have CC2 and we have RL. The output circuit can be represented like this, and this is V0. All right. Let the input circuit remain as it is. We have to calculate the gain. The gain A, now A is a function of frequency omega. So, we say a function of frequency, all right, and since we are considering low frequencies, we say A L omega. This L stands for low frequency gain. In the previous case, when we calculate the mid-band gain, we should have written a subscript of M, but one prefers to write A0. This is conventional. At mid-band gain, where it is a constant, you write A0. So, AL omega now is V0 by Vs, and this is the circuit that has to be analyzed now. Input part is this, output part is this, and the analysis can be done by inspection, just by looking at the circuit, because you see V0 by Vs can be written as V0 by V multiplied by V by Vs. Now, let us look at this circuit once again and calculate these two quantities separately. Our equivalent circuit, let us draw it again. Vs, Rs, CC1, R pi, and this voltage is V. Then you have, no, I am sorry, GM V RC, this is a voltage generator now with this polarity minus plus, and RC CC2 RL, and this is V0. You can see that V0 is equal to minus GMV RC, all right, minus GMV RC, then a potential division between RL and RC in series with CC2. Therefore, it would be RL divided by RL plus RC plus 1 over j omega CC2. Is that okay? I write this by inspection. Okay. Now, I can do a bit of simplification. You see, minus, let us write V0 by V. This is what I want. I want V0 by V. So, let us write V0 by V. This is minus GM. Now, look at the simplification. I have RC RL, RC RL. Then from the denominator, let me take RL plus RC out. All right. Then I get 1 by 1 plus 1 over j omega CC2 RL plus RC. Is that all right? Now, don't you see that this is simply the parallel combination of RC and RL? And therefore, I can write this as minus GM R0 divided by 1 plus, now I introduce a term omega 1 2 by j omega. I introduce a term omega 1 2 where I define omega 1 2 as 1 over CC2 RL plus RC. You see, the definition is that it is inverse of the time constant of the circuit. What is the time constant? Product of capacitance and resistance. RC and RL are in series, and therefore the time constant of the output circuit is given by CC2 RL plus RC, and the reciprocal of that I give the symbol omega 1 2. Then my V0 by V becomes minus GM R0 divided by 1 minus, now I take J up, 1 minus J omega 1 2 divided by omega. All right. This is the low frequency gain as far as the output circuit is concerned. We have, however, a task of finding V by Vs, and if you notice the circuit as I had drawn earlier, V by Vs is simply a potential division between R pi and Rs and Cc1, and therefore I can also write that down by inspection, that is R by divided by R pi plus Rs plus 1 over j omega Cc1. This I will now write as R pi divided by R pi plus Rs, I take this out, all right. Then I can write 1 divided by 1 plus 1 over j omega Cc1 R pi plus Rs. Any objection? Is that true? Have I distorted anything? Not yet. Not yet. All right. So I write this, I prefer to write this in the form R pi divided by R pi plus Rs 1 minus j, 1 by j is minus j, and then I write omega 1 1 divided by omega. All right. Omega 1 1 divided by omega, where omega 1 1 is now defined as the time constant of the input circuit, reciprocal of the time constant of the input circuit, which means Cc1, input circuit as Cc1 in series with Rs plus R pi. All right. This is omega 1 1 is defined as the reciprocal of the time constant of the input circuit. All right. Now, if I substitute these two values, that is V0 by V, this expression, and Vs by V by Vs, this expression, then I multiply the two, then I get V0 by Vs, that is the overall gain, and this obviously V0 by Vs becomes equal to, if you notice carefully, minus Gm R0. I take the constant term of the other expression R pi divided by R pi plus Rs, alright. Then I have two terms, 1 minus j omega 1 by omega, 1 minus j omega 1 2 by omega. Is that clear? And if you notice the constant term here, you see that Gm R pi is beta, and therefore this is minus beta R0 divided by R pi plus Rs times 1 over these two terms. This is A L omega, the low frequency gain as a function of frequency. What do you recognize this as? This is the mid-band gain, that is A0, and therefore the normalized gain, that is AL omega divided by A0. If we normalize the gain with respect to A0, it is simply given by 1 by 1 minus j omega 1 by omega, 1 minus j omega 1 2 by omega. It is a product of two terms like this, and you notice that if omega, what is the value at omega equal to 0? Obviously this is 0, and as omega increases, the gain increases. When omega becomes large compared to omega 1 as well as omega 1 2, the gain becomes 1. It simply becomes 1, right? And therefore it does explain the rise of gain from 0 to the mid-band value A0. The question now is, where is omega L? What is the frequency at which the gain is 3 dB down the mid-band value, 3 dB less than the mid-band value, or 1 by root 2 times the mid-band value? Well, strictly what you have to do is, you have to take the magnitude and equate that to 1 by root 2. You will get a quartic equation, omega to the power 4. Engineers don't like to solve equations. Electrical engineers in particular try to find a shortcut. What they do is the following. He says, all right, I have two frequencies, omega 1 and omega 1 2. Suppose they are several times apart from each other. Let us say omega 1 is greater than omega 1 2, and maybe this greater than is, let us say, of the order of 3 times. What is the square of 3? 9. And much greater than means in electrical engineering is 1:10. Now in this case, you see, when I take the magnitude, what is the magnitude of this term? Square root of 1 plus omega 1 by omega square. Now the other term is 1 plus omega 1 2 by omega square. If one of these terms is approximately 10 times the other term, then obviously one can ignore the other term. And this qualitative argument, it can be strictly put on quantitative terms. This qualitative argument says that which one
Can you explain it again? Because we are multiplying the, yes sir.
Yeah.
Subtracting or adding sir.
Okay.
Multiplying.
Let us consider the value. Let us say that omega 1 is much greater than omega 1 2. Let this be the case. Okay. Let this be the case. Then at omega equal to omega 1, what is the value? What is the magnitude? Magnitude is square root of 1 plus 1. I am sorry. Yeah, 1 plus 1. Okay. And the other one is approximately 1. And therefore omega 1 determines the low frequency cutoff. Is that clear? This is the point that I was making. If one of them is much greater than the other, I will come to what is much greater a little later. If one of them is much greater than the other, then the greater one determines the low frequency cutoff. Now, how much greater? In practice, 3 times is good enough, because the quantities involved here not as omega 1 1, but omega 1 1 squared. All right. So, if one is 3 times the other, 3.3 times approximately, then the squares shall be 1 order of magnitude apart, and therefore 3 times greater is good enough. All right. So, what one does is the following. Given a circuit, if you see that omega 1 1 and omega 1 2 differ by at least a factor of 3, then you take the higher one as the low frequency cutoff, as I have shown you here, the higher one. All right. On the other hand, if they are comparable, if this much greater than sign does not hold, suppose they are, one of them is 10 Hertz and the other is 15, then you have to solve this equation exactly, the quartic equation. There is no other way. But that is hardly ever the case. What an engineer does, engineers like you, IIT graduates, they design. So, you are told by the boss, we want a high fidelity stereo amplifier whose low frequency cutoff is, let us say, 5 Hertz. You are told that audio frequencies go from 16 Hertz to 16 kilohertz, but if your amplifier satisfies only this, the drums, the left-handed, the baya in particular, which is a very rich in low frequency, that sound is lost. All right. If you want a very high fidelity stereo amplifier, then you must go down to about 5 Hertz as the low frequency cutoff. All right. You have to design an amplifier with 5 Hertz cutoff. Then what you do is you find CC1, okay, you find CC1 prime, let us say, from whatever the specified omega L is. What is omega L if the low frequency cutoff is 5 Hertz? What is the value of omega L? What?
5, sir?
No,
10
omega
pi.
L.
10 pi.
10 pi, 2 pi times 5, you must not make a mistake. So, what you do is, from the specified omega L, you find out CC1, the coupling capacitor 1, which would be omega L times, what is the resistance? Rs plus R pi. You calculate this capacitance, all right. Then you calculate the other capacitance, CC2 prime. Are you following the design process? Given, if the omega L is specified, you calculate the necessary values of CC1 and CC2, each satisfying this value of omega L. How do you find CC2? Note, I am not putting CC2, I am putting CC2 prime, because the design values will be different, all right. So, what I do is CC2 prime, I also calculate from the same omega L. I say omega L, what is the resistance as I said? RC plus RL. Then from these two, I find out which one is larger. Suppose CC2 prime is larger. If this is larger, CC2 prime is greater than CC1, then what I do is I put CC2 equal to CC2 prime, whatever the calculated value is, all right, and I increase the other capacitor at least 5 times. 3 is a good figure, but to be on the safe side I increase 5 times. What does that mean? It means that omega 1 1 shall now be at least 5 times less than omega 1 2, and therefore omega 1 2 shall determine the low frequency cutoff. Is the design process clear? We shall illustrate this by means of an example. Mind you, we have not talked about CE at all so far. What will be the value of CE? Well, we'll consider that also in a moment, but let's consider an example first. Suppose you are given an amplifier in which Rs is 1K, the source resistance is 1K, the same design data, but to bring variety, let us say R pi is 2K, Rc is 4.5K and RL is 9K, GM is let us say 60 millimho. What does this correspond to? I sub C? Yeah, so what is I sub C? 1.5 milliampere. If GM is specified, then you know what is I sub C. If I sub C is specified, then you know what is GM. GM is 60 millimhos and CC1 and CC2 both are specified as 1 microfarad. You are required to find out A0, that is the mid band gain, and omega L. Alright, this is not a design problem, this is an analysis problem. Now obviously what you can do is A0 is minus beta, if you remember, R0 divided by R pi plus Rs, and you simply substitute. Is beta given? No, beta is not given. R pi and GM are given, so beta must be 120. Is that right? 60 times 2 is 120. K and millimho, they cancel each other. 120. R0 is 4.5 K parallel 9K. Divided by R pi is given 2. I have kept it in K because it will cancel. 2 plus Rs is 1. So I can forget about K. What is the parallel of 4.5 and 9? Oh, it's 3. So 3 by 3, this is simply minus 120. Then with the given CC1 and CC2, calculate omega 11 and omega 12. Omega 11, as you know, is 1 over CC1 R pi plus Rs, and omega 12 you calculate as 1 over CC2 Rc plus RL, and doing this calculation one finds that omega 11 comes as 333.3 radians per second, and omega 12 comes at 74.1 radians per second. Well, this is about 5 times, isn't that right? This is about 5 times this, and therefore your omega L is equal to 333.3 radians per second. All right? This is an example of analysis. Now if you want to design, we'll consider the design problem along with that of emitter bypass capacitor, and it is at this point that we shall take a 5-minute break. We reassemble at 5:00.